Actually, it's not only important because it's today's tutorial. I think getting a structure for your system, material, molecule, whatever it is typically the first task that you have to solve if you want to do a calculation on whatever, right? And it's also not the last talk today. Mateusz will right after me give the introduction to the tutorial. So again, why is this important? It is important because we typically have a question when we start our computer, right? We go there and there are such interesting things like, for example, in which stoichiometries do these two components form a crystal or form complex, bind each other? This is something that we sometimes want to be able to say. Or something that I at some point wanted to know, how does the gas phase IR spectrum of such a peptide with a lithium cation looks like? It's a question that one can ask. And so on. And there are many. I mean, you have different materials. You want to compute the property of a material, for example. But in order to do that, in order to perform the calculation of a spectrum or several calculations in order to obtain a spectrum, the first thing is you have to find a structure for that. And the nice thing is, if we do things with a computer, is that we in principle have the chance to do things faster and sometimes cheaper than experiments. I say sometimes because typically when you start something, you will realize, it's not accurate enough. It will take you a lot of time in order to develop a right workflow to compute a certain property. And also the faster thing is typically not true. Also, I mean, I have colleagues that measure these IR spectra. They are amazingly fast with it. It takes an afternoon, and then they wait for half a year until we can get back to them. Also, Mateusz knows that tale quite well. What is really cool about simulations, what I like a lot, is that in principle they can map uncharted territory. And so essentially, this is also a bit in the spirit of what Matthias was talking about in his introduction here, is that there's so much chemical and material space that we did not yet investigate, but that will eventually give interesting materials and properties that we could need. And this we can really kind of tackle with predicting structures and properties of such new materials. And we can explain some unresolved experiments. So typically what happens is that your fellow experimentalist comes to you and says, I have this spectrum or this whatever type of number. What does that tell me? And then you're supposed to compute something. You're supposed to recompute exactly this observable and help him explaining this experiment. So that means that you have a given system, a molecule or a material. Then you create a model for that, and then you compute this number. This is typically not very easy because there are many things that one has to do on that way, right? I mean, first of all, we need to have a structure. And this can be, if it's a simple rigid system, we can just draw that. For a simple molecule, let's say benzene, I don't need to do a structure search. I can draw that and I can perform a local optimization and it works. But if it gets more complicated, more degrees of freedom, more involved system, then we have to either be lucky that someone, for example, an experimentalist has solved the structure and deposited it online, or we have to find it, for example, in databases for electronic structure calculations like the NOMAD dataset. And then we can start from there. Or nothing is known and we have to perform a structure search. So that means that we have to generate many structures and find the right three-dimensional structure for this system, right meaning right for a given energy function. And this is the next problem. We have to rank the multiple models with somehow an energy or fitness-based ranking. We have to decide, is this the structure or this the structure? And this needs an accurate enough energy function. And then, after all, we can compute a property for this material or molecule and go back to our experimental colleague and say, we found this, and typically they don't agree. But sometimes we are lucky. But the only thing that I will talk about today is exactly this generation of 3D structures. The thing is, this is a fairly big field, and I will essentially cover only a very small amount of that. I will neglect many very important works and contributions. It's just to give you an idea, a glimpse on this. I mean, one can do like a 1 or 2 week workshop on that. So, and this I can't cover. You don't want to listen to me that long. Just a few things. We search dominantly on the potential energy surface here, but not always. There are a few approaches where we would search on a free energy surface. So, and this is, I think I don't really need to repeat that where this comes from. What is interesting on the potential energy surface for us here in this talk is in particular the global minimum, but also local minima around the global minimum. Often you would like to have an ensemble of low energy structures because you never really know which minimum for example, the real world system is in. And attraction basin I will explain later in more detail. So searching, this is essentially a bit related to local optimization, a topic that was covered already by Oliver Hofmann on 2 days ago. So where really local optimization going from one point to the closest local minimum is meant with. And what we will do today is global optimization, so finding minima on the overall potential energy surface. Luckily, Oliver also gave a bit the outline of today's talk already in his talk. So he had this one slide on global structure search, and you already see that this covers quite a number of topics. There are even more, and I will not even cover half of that. But there are two things that are to be covered in the workshop later on. So really a detailed introduction to molecular dynamics and also statistical mechanics will be given tomorrow by Luca and Mariana. And then a talk on cluster expansion is a talk and also a practical session on cluster expansion is scheduled for next week, Tuesday, performed by Santiago Ricamonti and Chris Sutton. So these things will come. So what we do, again, just we are still in the introduction part, is that we want to sample such a fairly complicated energy landscape. So you see that there are many ripples, it's a very rugged landscape. But the nice thing is that it has a tip. So it is this characteristic of a funnel that is often, not always, a feature of such energy landscapes is something that helps us in eventually finding the global minimum. If this would not be that deep, if many minima have a very similar energy, searching becomes way more complicated. No? But typically, stable compounds or molecules have such a funnel-shaped energy landscape. And again, the problems that we are confronted here are how to rank multiple models in order to predict which one is the global minimum, but also how do we describe the system in the best way? This is a problem that we face when we want to represent an energy landscape. No? Which is easy. So something like that is like a reaction coordinate for a reaction. You have just one coordinate and then you go over a barrier. But flexible molecules, or also fairly complicated materials, typically have multiple degrees of freedom. And the potential energy surface is these degrees of freedom plus the energy. So high-dimensional hypersurfaces, or if you want to call it. But this is also important for sampling, because we want to sample all the relevant degrees of freedom for such a system. There are different, so these are some choices that we have to make when we are devising a search technique, so in kind of automated way, an algorithm to sample such an energy surface is, first of all, the coordinate system. So we need to find a way of representing the system that allows us to comfortably browse these degrees of freedom. There are different choices. Cartesian coordinates is essentially a standard format of how you exchange structures. A bit nicer for structure searches, when you look at molecules, are these internal coordinates. We will look like that. And there are also a bit more exotic things like natural coordinates, which we don't cover. Then, of course, there's the question of the objective function. So objective function is essentially the thing that we want to optimize, right? We want to find a minimum in a certain function, the global optimum there. And typically the objective function for us is something that gives us a potential energy. It can be an empirical potential, a density function theory calculation, or something else. But you can also optimize other things, like a band gap, for example, which we will not do here. And then there's, of course, the choice of how we want to search. And there are multiple different methods, many different methods, and even more different classifications of these methods. This is a fairly simple one. We can search systematically. I will explain you in a second what I mean. So we discretize our degrees of freedom and sample them. There are deterministic search techniques that I only list here for completeness. Deterministic means that you know that you have found the global minimum. However, I have not seen really a good implementation for that for molecular or material structure search, because we have coordinates that depend on each other, while these techniques work dominantly on independent coordinates. And there are stochastic and heuristic searches, which essentially means that you never really quite well know if you found the global optimum. But you get hints from the course of the structure optimization. So we have a list of demands on a good search technique, a good way of finding such a global optimum. First of all, it sounds trivial, but it must be able to find the global minimum. That's the first thing. Unfortunately, we can't say when. It must be able to find, but also to leave local minima. So when we run around, we find a cozy place, but we should not stay there, because there's an even more cozy place elsewhere. So we still should have enough energy to leave that again. I don't quite know what I wanted to say with that one, but what is important is to explore conformational space fast, because computer time is limited. If we use an accurate energy function, for example, DFT calculations, one optimization or one energy function call can take minutes. And if you have to do this 1 million times, this is a considerable number of CPU hours that we would waste on that. We should ideally also not blindly jump around on the energy landscape. We should use kind of the knowledge that we accumulate in the process of the optimization. So we have sampled already a few areas. So I know that these chairs are good. But I don't need to sample here longer. I can go there now. No? So we have to keep this in mind, or the algorithm should keep it in mind. And we should avoid complete enumeration, because that means that we are not faster. The goal of using such a heuristic technique is to be faster than a complete enumeration or a totally random enumeration, right? And we should avoid revisiting known regions of that conformational space just for saving computer time. Okay, so again, briefly on representing molecular structures. So here, for example, you have aldehyde, and this is just the sum formula. It doesn't tell us much, and they are isomers. So, for example, we can represent it here in such a SMILES code. I put the SMILES code in particular here because it will also be one thing that you will see in the tutorial in the afternoon. It's just a one-line notation for mainly organic molecules. So if you write things in one line, it means that they are linked to each other. So C is linked with a single bond to the other carbon, which is then linked with a double bond to oxygen. So this part is represented with the SMILES code, and then you only add the hydrogens until the valence criteria for carbon is fulfilled, so to say. So, and this leads us here to the Lewis formula, and until now we don't have a structure yet. This is just a chemical drawing, it's 2D, it doesn't tell us much. But then we know that molecules are 3D things, so in our computers they look like that, and in order to make them look like that, we need to give them coordinates. And these coordinates can be something like here, this set matrix. What is important here is that we describe, so to say, the molecule internally with internal coordinates. That means we have distances between atoms, we have angles between atoms defined by 3 atoms. So, for example, these 3 atoms here, oxygen, carbon, hydrogen, they have an angle between them. And third, we have torsion angles that are described by 4 atoms. So we have 2 planes of 3 atoms each, so here H6, C4, C1 is one plane, O2, C1, C4 is the other plane, and between these 2 planes we have an angle, that's a torsion angle. And it represents the rotation around this bond here. No? If you now think about what describes the overall structure of that molecule, then it's not the atomic distance, because this doesn't change for an intact molecule. It oscillates merely around an average value. And similarly, also the bond angle doesn't change. It also might slightly be oscillating. The overall structure is solely defined here by this torsion around these two, around the bond between the 2 carbons. That's why this is also a fairly nice coordinate for us to search in. No? This is just for comparison. The set matrix, so these internal coordinates, can also be rewritten into Cartesian coordinates, which is typically the format that we use when we make input for example, a DFT calculation. At least with FHI aims, that is the only way of putting the molecule in there. what do I want to say? Exactly what I said already. So the torsional degrees of freedom define the molecular 3D structure, while the bond lengths and angles only oscillate about a midpoint. So what do we do with it now? We can do systematic searches of such a molecule. Systematic is exactly as it is drawn here in a very elegant way. We just define a grid, and then we just walk around the conformational space. Then we step aside, and we walk back. And by that, we will find everything. No, we will not. In the moment when we make the spacing too big, we will miss things. If we make the distance between our tracks here too far, we can easily miss one of these sweet spots here. No? So this technique, like a systematic search, can nicely be performed for fairly small molecules. This here is let's say it's a classic. It's the alanine dipeptide, which has two defining torsion angles here, phi and psi. And you can sample them completely, essentially. You can discretize them. As first, you identify these two dominant degrees of freedom. Then you discretize them, for example, a 5 to 10 to 30 degree step. And then you generate all the combination of these two torsion angles and obtain an energy value for them. And then you can make such a nice contour plot that will tell you where the minima of this molecule or the minimal structures of this molecule are, and also where the global optimum here, the C7 equatorial structures, also to be found. If I'm correct, this is also the example that you are going to compute in the tutorial this afternoon. So this has been done since the early 90s. So John Poppel was and his group, and with Teresa and Mark Head Gordon, both are also still famous, I would say, have done the first proper Raman-Randran plot of this type, and until now still people recomputed with ever improved energy functions on the basis of that. So the systematic thing, however, works only to a certain point. So here this is again like 2 degrees of freedom, but if we make the molecule longer, we get more of these degrees of freedom. And we see that also if we discretize, the number of options that we have to consider, the number of points that we have to consider, still constantly increases. At some point it's not feasible anymore when we have a really long chain of carbon atoms, for example. So what do we do then? So the way to go is what one still has to do, one has to generate a structure model first, and then you evaluate an energy. But since there are so many, you have to put certain constraints on it. So we, for example, can say, so this is a biopolymer. We know that these things have often periodic structures. Periodic means that the subunits that you see here that repeat have the same conformation. So we only allow such structures allow only structures with periodically repeating backbone conformations. This might even still result in a fairly high number of possible structures. So the next thing that we would do before we actually do a DFT or force field calculation, we first check if the whole thing at all makes sense, if it's a sensible structure without clashes between atoms. Because those we can directly discard, they are not useful. And the next step is we are interested in a certain property. So we only want to find, because our experimentalists said, oh, these things are hydrogen bonded, we only want to have structures that have a certain hydrogen bonding pattern. This is what these arrows here indicate. And only if this is also satisfied, then we go into then we put the structure into our DFT calculation. So a good way of sampling, especially if you want to do it accurately, is to first get rid of everything that anyways doesn't make sense. No? You save a lot of time by that. So, and what I have illustrated here, like this restriction or this focus on certain type of structures by hydrogen bonding, can also be done with other things. I mean, when you have a material, you might have an idea about crystal structure or space groups or whatever, or symmetries. These are all constraints that you can put in the generation of the trial structures. No? Or you use chemical intuition, which is often dangerous. So what we did in this case was we, by that, obtained like a nice overview on the helical structure of this type of beta peptide structure. In some sense, it's some type of nylon derivative, which is cool, and it also makes sense. But the thing is, what we've learned here is only the relative energetics of a subset of conformational space, right? due to putting in these constraints, we don't know how these structures here relate to the rest of the possible structures. Are they more stable, less stable? Here, experiment says it's okay, because this is the structure, for example, that is dominantly found in experiments, so the prediction was fine here. No? But still, by restricting your search space, you might end up in searching in the wrong area. So what is next? So in order to avoid it, in order not to have to restrict so much, there are now these more heuristic search techniques. One thing that is advocated is basin hopping or minima hopping, so mainly dominantly by David Wales or also by Stefan Gödecker, that are both developing or have been developing methods in this area a lot. The basic underlying idea of this is this attraction basing concept. So when you look here at such a potential energy surface in a nice 3D representation, you see that there are distinct points. I mean, when I'm at this point, I will fall down into this minimum. When I'm at this point, I will fall down into this minimum if I let loose, right? So that means that every point that after local optimization ends up in this minimum belongs to this attraction basin. No? So that means that we can reduce this landscape to these areas. So everything here is part of this yellow attraction basin. And we give it, in this example, the energy value also of this minimum here. No? And if you look on top, it can look like that, essentially. So attraction basins. So in this you can search by something called basin or minima hopping. In principle, it's a fairly simple algorithm. You start with a structure, first a randomly generated structure or whatever you want to do, and you perform a local optimization. You end up in the next local minimum that you reach here. And then you escape from that minimum. By some way, you go to another place. So you are here in this minimum, you project out of it, and you fall down to the next one. And you repeat and so on until you have found all minima, ideally. This projection is what essentially also defines the differences between these methods. You can do this by projecting along torsional modes, you can do random movements, or you can do molecular dynamics trajectories, as it is done in the minima hopping by Gödecker. And this is, in a sense, the pseudocode for this minima hopping algorithm that is that was developed by Gödecker. I directly copied it from the paper. Looks a bit complicated if one has to spontaneously read it, so I give a bit of a guided tour through it. So the first important thing is this escape. So the first is this escape trial part. So that means that you start at the point where you are, at the minimum, you give this current minimum, you give the system a bit of energy and let it evolve in an MD simulation. And this you do until the potential energy that you get in this MD simulation briefly peaks, it gets high, and goes down again. And this is the moment you stop the MD and do a local optimization, hoping that you end up in the next local minimum. The next thing is you have to evaluate. You have to check whether you were falling back to the previous, back to the current minimum, if you fell into the previous minimum, or if you are in a new minimum. And then you can decide if you accept this minimum. No? Accepting means if it's lower in energy, you definitely accept it. But if it's higher in energy, you might want to reject it. On the other hand, there are also certain high energy minima that can be seen as hubs on the energy landscape. So from this minimum, I could jump there, or I could jump there. And both could be beneficial. So sometimes it's good to revisit certain central points of such a complex landscape. So in that sense, you often sometimes accept also so-called uphill moves. No? And then there are, of course, things that you can adapt there, where you can tune a bit. So you can, for example, tune this kinetic energy here. This is the energy that you give the system in this initial MD simulation, or this escape MD. If you kick it harder, it might fly farther away. You constantly adapt this energy also over the progress of your simulation in order to ensure a certain convergence at some point. Or if it gets stuck, to kind of make more wild moves leaving certain areas of the structure space. And you can also constantly adapt the energy difference for the acceptance. So for example, maybe accepting uphill moves. No? This can be applied to many things. Gödecker did this with a silicon crystal, but it also shows that sometimes these optimizations can be quite complicated. So this is the input, this is one of the input structures, which is the correct crystal structure, but it's rotated with respect to the lattice vectors. No? So this is the global minimum. The problem here was really to go over this barrier, because there's no, the only way of getting there is via an amorphous high energy structure. And this is a fairly complicated case for an optimization. As you see here, this is a plot about the progress of such a minima hopping optimization of such a silicon crystal. And you see, for example, that there are these wild jumps in the energies. This is the point where the algorithm kind of increases the kinetic energy in this escape MD part. And also where you increase this EDIF, so this acceptance of higher energy structures. And only after a fairly long simulations we end up here in a converged point. And there you see also one of the big problems of at least this implementation when you would like to use it, for example, with a DFT calculation. The problem is that each of these trials here contains a certain number of steps of local optimization. No? So local optimization into the next minimum as a start, and then for the escape part, you again do multiple steps of MD simulations. And these are already millions here. That means that you have, let's say, if you are conservative, at least by a factor of 10 more of that, energy function calls and force evaluations that you can easily do with an empirical potential, but which start to get quite painful if you would like to do this with a DFT technique. No, so that's sometimes a bit the problem when using MD as an escape step in such Bayesian hopping algorithms. That doesn't work well with more involved energy functions. What's my next slide? Yeah, another technique in order to sample is, of course, molecular dynamics. And you see already this will be really the basics of MD will be covered tomorrow by Mariana and Luca, and I don't want to I don't want to do that instead of them. So, but what we do is, what one in principle does with the MD simulation, you watch how a molecule or a system evolves over time, so how it moves essentially at a given temperature or at a given energy over time. And with that, it moves also through its structure and conformation space. And this is one thing that one can use if you want to sample structures. So one way is, for example, a simulated annealing type algorithm in which we stepwise decrease the temperature that the system has. No? What we do, we start with a structure, we randomize it, and then, for example, if we implement this as a Monte Carlo algorithm, decide on the acceptance of this structure using such a metropolis criterion, where the difference of the previous and next energy is considered, and also here the temperature. And how high and this acceptance is then based if we reduce temperature over the course of the Monte Carlo algorithm. We also decrease the acceptance of uphill steps. So at some point we force the system to converge. This can also be implemented as a molecular dynamics simulation, where we really make as a step obviously these MD steps from one to the other, and then stepwise cool the system down in an annealing type simulation. This can also be, and sometimes even increase temperature again, so we temper it. No? So this is a little bit also nature inspired. This is the way you treat typically steel or certain materials, where you temper it in order to get it to a very stable, good conformation. This tempering idea is also used here in this replica exchange type of MD simulation. So where you have multiple instances of your simulation running simultaneously at different temperatures, and then you exchange between them also again with some with a metropolis criterion. The interesting thing is that first of all, due to these changes in temperature, you sample. No? When you heat it up, it moves more widely and it has a higher chance of going over a barrier, and you occasionally freeze out in order to reach a local minimum or a certain basin. No? But on the other hand, by coupling them with this metropolis criterion, you can link them, all the simulations, to each other and finally, and this is something that again probably Luca will talk tomorrow about, get also an idea about free energy. So this is the nice thing about replica exchange MD. It really gives you access eventually also to free energy properties which we typically neglect if we do just potential energy surface sampling. No, we generate a meaningful ensemble of conformaires. We have a very much improved sampling if we compare to a classical, also not class, to a normal molecular dynamics MD molecular dynamics simulation. And what is also nice, we do not really have to put in any assumption about the important collective variables of the system. We just put the system in and let it evolve. We don't say this torsion angle is important in this one, we just let it run on its own. The problem still is that many force evaluations are involved, which makes it expensive, and also MD typically stays at the stays around. It doesn't necessarily move over the conformational space. We are mainly sampling known territory. So what can we do about that? So all this use of molecular dynamics, being it as escape in this basin or minima hopping or in, for example, replica exchange MD, involves many of these energy function calls. That means it's tough to do with the DFT calculations. I mean, when you do it with DFT, you do maybe 100 picoseconds for a fairly large system, and this is probably often not enough. So the question is if we can do something else. And one option is this ab initio random structure search thing that I kind of like, and Matthias has to smile a bit, which Picard and Needs essentially pioneered, where really we base the search on random. Now my pointer died. Where we really base the search on so where the search really only happens by randomly jumping around on such an energy landscape. So this was, I would say, pioneered by Picard and Needs, and it's a fairly simple algorithm, as you can see here. So we generate a random model, and then we perform a local optimization with our preferred potential. But it's not that simple. Over the time, so this is the simple idea, and it's really cool to implement. It takes you 20 minutes to do, eventually. But they performed, of course, a few more checks. I mean, first of all, you generate a random model, and then you check, is it sensible? Does it produce clashes in the molecule or in the material or not? If it's not sensible, then you do again. If it is okay, then you perform the local optimization. But still, you can do even more. So you can, for example, define boundaries for randomness. So if you, for example, think you can define a minimal value that you allow for bond distances, because the area of the potential energy surface with really close contacts between atoms is fairly underpopulated with minima. There is essentially nothing, so you avoid that simply. Or you only consider a certain type of unit cells or symmetries, chemical intuition, whatever. Also, things that come from the experiment you can put in here and define boundaries for the random generation. And the next thing that one can do, once one has found nice low energy minima, you can also focus on this area, so to say, and essentially switch from this random sampling to a basin hopping like scheme, because they also then do these MD steps in order to shake the system out of a given minimum, right? So in that sense, the initially very simple algorithm of random structure search got a bit more involved. No, but it seems to work. This is an example from their paper. So really just, this is one of these runs, so to say, that they have performed by randomly placing 60 atoms in a cube, checking if they clash or not, and if the connectivities of the carbon atoms are making sense. So there are threefold here, so threefold connections of each carbon. They created such an input structure that one can easily, apparently, locally optimize into such a small C60 buckyball. So this is kind of the idea here. So this ab initio random structure search has uses a few characteristics of the potential energy surface. As I said, it's practical that, for example, the fraction of the PES with really short bonds, it does not contain any minima or hardly any minima. So by that, you can avoid sampling it with this structure check. One of the important things is that deep and there with global minima or eventually global minima have typically the biggest attraction basin. So that means by randomly throwing at them, the chance that you end up there with a local optimization is fairly high. So that means that essentially the randomness hits quite often good results. And then the next thing is also that you expect typically low energy basins to be close to low energy basins. So once you have found an area of fairly low energy, it's very likely that you will find good or better candidates around it as well. So this is why this shaking part, so this switching to this basin hopping helps at all. So in the end, one could say that it's maybe random, but it's random with boundaries that are based on whatever you can put into such a search, right? Okay, what's the next thing? Then one class of search techniques that we briefly discuss here are genetic algorithms. When you hear genetic, you see already that has something bio in it. So it is also in computer science, there's this class of bio-inspired algorithms. So something that was inspired by seeing how nature does things. One example you have seen already, simulated annealing is such an example. So this is, they go into a low energy state by tempering a steel, for example, or glass, and get it into an even better configuration. But also you can see how, for example, life works, how evolution happens. And this is what the genetic algorithm is about. So the basic ingredients here is a genotype. So one individual, each of us has genes. And they are here, in this case, placed on a chromosome, or we call it a vector if we want. And our vector consists of 6 genes. No? And these 6 genes define, in the end, the phenotype. How does this nice little ladybug look like? No? How long the wings are, if the coverage of the wings is fine, if it has a head or not, how the eyes work, and so on. This is in our genes. I need glasses, and that is unfortunate because some of my genes might trigger that. No? So, and of course, animals or our genotypes are not alone. They are typically in a group, in some sort of a population. And this is our population at generation n, at a certain generation. And then, of course, as life is, there will be a next generation. And this next generation happens to be there because of them here mixing together, some of them dying, some of them living a bit longer, some of them having children, some of them having no children. And this, in the end, gives the next generation. And then on and on and on we go. But this doesn't happen in thin air. No, it happens with an evolutionary pressure. No? There is something. There is a selection mechanism. So it's really hot. If I can't regulate my body temperature, I will die early. So I will die out. My genotype will not be there in the next generation anymore. And this is essentially, this way is what we use in such a bio-inspired algorithm. No? We implement this in a computer code. How we do that is, for example, for a molecule, we have here a molecule. I already told you that we like to sample over torsion angles. So these are the ones that are here highlighted. And this we can encode here in our vector. And as an evolutionary pressure, we simply use energy. We want to optimize energy, low energy, high fitness, so to say. And what we then can do, we generate a population of conformations encoded here with these values for the torsion angles. And then we perform the genetic algorithm part on it. We modify them, right? We can perform, for example, a mutation. We randomly change one of the values here from 60 to 45 mutation. Or we can mate 2 of these chromosomes or vectors and perform a crossing over between them. So we exchange here one part We define a cutting site in this vector and switch these parts between these two vectors in order to generate an offspring. And this is then again ranked according to fitness, according to a DFT energy, and we see which of them essentially wins and is able to proliferate. So this one can implement in an algorithm for structure search. This is something that Nair and Goodman have done in '98. So they start with a random pool of conformers, and then on this they perform these genetic operations. So they make crossing over between individuals, and they make mutations. And then they make this survival of the fittest thing. So it's about Darwinian evolution. So only those are transmitted or brought to the next generation that match certain criterion, for example, a low enough energy. And then there's some point the decision if we stop or not. We don't stop, so we go again and again and again and perform many generations with our genetic algorithm, and then in the end get out a list of all the structures that were found. If we do this with a DFT technique, as you see, this is really so all the optimization work is done by the genetic algorithm. So each coordinate of the system has to be handled by the global search technique. This is nice for some things, but not for all. For example, using DFT as an energy function, essentially having a very continuous search space, this doesn't work well. And for that reason, one adds here a local optimization step. No? So you are at a certain point, and then you fine-tune by performing a local optimization. And in addition, what you maybe want to do is to add some sort of a blacklist in order to avoid recalculating things that you have done before. You know, these are the things that you would, for example, do if you do such a search with an expensive energy function. In the end, that means that we are not doing Lamarckian, not doing Darwinian evolution, where essentially a certain feature, a certain genotype dies out because the giraffe is simply not able to reach the tree. But we have some sort of Lamarckian evolution that means within a generation, by training, the giraffe can make its neck longer and reach the tree, and then is even able to inherit this property to its offspring. This is not totally true in reality, but it is something that one can implement, of course, still as a computer algorithm. So that is essentially the tool that you will use today. That's this Farfoum algorithm. So goal here was not really to only find the global minimum, but to essentially generate a low energy example, a low energy ensemble of structures. And this is just a comparison that Adriana did in her PhD thesis. What you see here, these horizontal lines are all minima of these respective molecules that we knew quite well already because they were in a data set. No? And whenever there's just a gray line, it means that Adriana's GA implementation has also found this minimum. Whenever there's a green line, it means that she has found one more, which is cool. Whenever there's a red line, it means that she missed one with her GA implementation, which doesn't happen as often as finding a new one. So kind of the algorithm seemed to work. And another very important comparison is actually this one. Just probably best ignore the black line, that is not so important. But we have here the red line is essentially performing a random search. And what we see here is the amount of structures that was found from a given total set. So we have set a set, or we have set 100%. 100% are all the structures that we know of this system. And then we see which algorithm, which approach, for example, the random search, finds most of them within a certain energy window. And we see that overall, without such an energy cutoff, the random search works better than the GA search. No? But when we lower this cutoff window, we see that there's a point where the GA takes over. So with the GA, with the global search technique, we focus, so to say, on the low energy structures, which is logical because in the generation of structures, we prefer properties or genotypes, so to say, that yield a low energy. No? And by that we focus on low energy minima. So what else? Yeah, so FAFUM is of course still being developed. This interface to a few of these programs, for example, and most dominantly FHIMs, but also to NWChem, probably to others as well. And there are currently things going on. I mean, Mateusz, this is already not so recent anymore. He has implemented ring pucker rings, which is nice for chemists. And Dimitri, who's also here and also a tutor today, implements further degrees of freedom that allow us to describe how molecules, where molecules are placed relative to something. For example, his project is mainly about how to place a molecule on a surface, in which orientation and in which position. No? So implementing more of these degree of freedoms that might be of interest. So one thing that we did not talk about yet is how do we decide that we are done with our structure search. And this is a very complicated thing. What one typically does is you monitor the energy that you reach, and if you didn't reach an improvement of energy over a long time, how to define long is also not easy, then you think now this search is converged. If you now take a look again at this example that we saw from earlier in the minima hopping, for example, there are a few plateaus. I mean, if you say that this amount of steps here is a long time, there was no improvement, you would have stopped there and said this is a structure, or maybe here, or maybe here, or maybe here. But no, only after, at the very end, even after very wild, already again increase in energy, one ended up in the global minimum. So deciding when such a heuristic search technique has converged is a hard task. Actually, it's not a hard task. One can't really say, essentially. No, so we are getting towards the end. So what I just shown you is this, we have an optimizer like the GA, and this gives a set of degrees of freedom to the fitness function, which then gives back the fitness. No? This is a fairly, let's say, a simplified way of such a, for example, GA. So this here could be such a GA algorithm. So that means also that there are many different things that one can do. One can use many different degrees of freedom, or also do different types of objectives, or follow different types of objectives here in such a fitness function. And so examples are also, I took pictures of posters recently. So one thing is that Timothy Rose has implemented in his GATOR, also he's doing that together with a few more people in Noah Marom's lab, is, for example, different types of degrees of freedom, like here really in order to describe optimal orientations of molecular crystals. So you are flexible in such algorithms in implementing new degrees of freedom. That is cool. And one other aspect on his poster that I find important, that is intrinsic to this type of search techniques, is that you can use it also nicely in a parallel way. So you can, like he did niching, so there are multiple populations around, and those you can nicely distribute on a computer. So you can use many different nodes, and on these nodes you can have, you can also in a parallel way perform multiple of these things at the same time. So parallelism is quite inherent to these search techniques, which is a nice feature. Another very nice poster that I found was from Torbjörn, and he also uses a genetic algorithm, but in a completely different way than I just have described. So he's not looking into conformational space, optimizing the total energy or potential energy of a system, but really looking, using a GA in order to essentially develop a material. So he uses anthracinones. This is here the anthracinone framework, so to say, as a potential scaffold to design electrode materials. And his fitness function are the positive and negative electrode potentials. So really not conformational energy, but really another property. And in order to find them, he defines his chromosome essentially with these 10 positions. And these 10 positions can be, I assume, taken by all of these substituents. No? And by that, he performs this genetic algorithm search here in the continuous line are kind of lower and upper bounds or Hull curves. And you see that with two setups of simulations, one time finding positive and the other time optimal negative electrode potentials, he can really find improved molecules for this task. So he's not searching structure space, but really chemical space. But you see also that these things are kind of intertwined. For example, when his molecule would be a bit more flexible, for example, we would cut here one bond, okay, then it loses its ability, but still, let's say we cut here this bond, then this part becomes flexible. And then, in order to compute one of these points, he would have to do a structure search to get that number, and then when he changes, mutates it, he has to do the structure search again and again. He would have to. That's the thing. No? So, but that's just to show that these things are fairly, so these type of algorithms can be used also for other problems. So that's the end, I think. What do I want to say? I'm also fairly in time. That's nice. So there's no single best search strategy. In the end, they all are, I would say, a little bit the same. It's always a little bit of random. All this searching and sampling only makes sense if you are at least a little bit sure about your potential energy surface. I mean, we can definitely, when we develop such a technique, we can use a cheap energy function because there it's just about how to sample. But if we want to use it for predictions, we have to use something reliable. And to be honest, currently I think empirical potentials for the systems that we study, the molecules that we study in our group, there's no good empirical potential for that. We have to use DFT methods. The longer and more sampling, the better. That's the only way of hoping to have found something. When you devise an algorithm, you saw, for example, in this minima hopping algorithm, you saw many of these little knobs where you can kind of adjust performance and speed. There one has to be careful. Settings that work well for one type of landscape do not necessarily work well for others. And then you will lose performance in the end. So robustness is typically better than high specialized performance. The question is also, what do you want? Do you really want to have only one global minimum, or do you are more interested in a low energy ensemble? Typically, the low energy ensemble is more meaningful in a real, also comparing to reality. So what we have of course, absolutely not have covered in this talk, and I will also not do that, but the next steps are, for example, when you have such a low energy ensemble, you would like to set these minima into relation to each other. So first of all, one relation you have already, the energy, you know the differences between them, but it's also interesting to know how they are related to each other in structure space, so to say. Are these two minima close neighbors, or are they very distant from each other? Are there minima in between them? No? And this is then interesting for the next step, namely the other type of interesting points on a potential energy surface are, of course, transition states. If I have an ensemble of minima, there's a chance of interconversion between them. And in order to get an idea how that works, I need to know the location and the height of the transition states. No? And this would then mean that I would perform transition state searches. There are techniques for that. And also, then after I've investigated my molecule, or it's such a structure space in a proper way, I have created many data points, and those I want to also represent in some way. I want to have a plot that puts all these points into relation to each other and allows me, for example, to understand that a bit. But this I will not talk about. So the last slide is essentially just a bit of literature that you might want to look at. So for example, here this is a nice paper about the ab initio random structure search by Picard and Needs. Or here's a pretty good recent, a very good recent review by David Wales that I would suggest. There's the original paper of Stefan Goetheker, and so on and so on. And here's also, this is a nice example about a structure search technique that I was not covering at all, if you want to see that, where we use replica exchange MD simulations. So with that, I'm sweating and at the end of my lecture.